we'll start next chapter, which is Gauss's law. So the first question that I would like to solve is relatively a simple one, but in some sense it's it's a good introduction. So let me draw the figure and then I'm going to explain it to you. So yeah, I'm going to use this color. So there's basically a conducting sphere at the center with a radius of A. Okay, so this is a solid sphere, but it's the whole thing, but it's conducting. And therefore, all of the charges are going to be distributed at the outer surface. And this is placed inside, again, a conductor, but it's a spherical shell with an inner radius of B, and an outer radius of C. Okay, let's give a charge to the inner sphere, the conducting sphere. Let's make it Q1, and let's take the charge of the outer sphere to be Q2. It's the guy which is they're concentric. Write it down. Concentric, and both of them are basically conductors. Okay, so this is a very nice example for Gauss's law, and what the question asks is the following: for this situation where there's a sphere inside and a spherical shell, calculate the magnitude of the electric field for various situations, okay? And those are, first, calculate the magnitude of the electric field, where the point that we're interested in is smaller than the radius of the inner sphere. So R is smaller than A. Part 2 is, obviously, it's between A and B, right? A and B. And you probably can guess what the remaining parts are. It's between now B and C. And finally, what is the magnitude of the electric field when radius is bigger than C? So it's 3 different regions. Calculate the electric field for those, okay? All of the charges are going to be concentrated the outer surface, the surface of this and the solid sphere. And this is going to attract equal amount of charges with a negative sign Q1 inside or the inner surface of this spherical shell. And since minus Q1 is attracted towards this Q1, since the total charge of the whole spherical shell is Q2, then the total charge of the outer shell or outer spherical surface is going to be Q2 plus Q1, so that when you add them up, you get Q2, right? So basically, let me repeat again, Q1 is going to attract equal amount of charge Q1 with a negative sign, right? Opposite charges. And because these negative charges go here, you will have a net plus Q1, which remains in the outer surface as well as Q2, since the total charge of the whole spherical shell is Q2. So I'm going to use this color for the inner sphere, okay? And the radius is A. And I'm going to use another color, and that's spherical shell. Okay, so I tried to draw it bigger. I don't know whether it's bigger or not. But okay, so these are the two guys, and this is B, and that is C. So we are interested in 2 different regions, so now I'm going to use this color. And the first one is when R is smaller than A. So we are interested in somewhere here. So I'm going to choose a Gaussian surface, which is with these dotted guys, and this is R. Okay, the Gauss's equation tells us the following: the flux, which is electric flux, E times dA, is equal to Q inside this Gaussian surface divided by epsilon 0, where this is a closed surface integral, right? So basically what we want to do is, for any Gauss problem, we don't want to evaluate this integral where E is inside. What you want to do is you want to choose the Gaussian surface so that you can take E outside of the integral, so that that E doesn't depend on any point on the surface. So that's basically it amounts into choosing an appropriate Gaussian surface, and after that calculating the enclosed charge inside the Gaussian surface. That's the whole Gauss's law idea, okay? And you can see that this Gaussian surface is a sphere, right? And any point on the sphere is exactly have the same behavior, and that's why you can take E out of the integral. So this becomes E magnitude, because they both are pointing along the same direction. The dot product gives you 1, cosine 0 is 1, and times dA is equal to Q enclosed over epsilon 0, okay? And for any Gaussian surface, I did it for this R smaller than A, but even if I choose the other ones, like in part 2, if R is between A and B, you see, still the same story. You know, the same E times dA is equal to Q enclosed over epsilon 0. Now Q enclosed is different. And if you choose R to be between B and C, you choose this Gaussian surface. And if R is bigger than C, you choose this Gaussian surface, right? Okay, so for all of these different situations, we will use exactly the same expression here. And for all of them, this dA is nothing but a sphere. And this gives you the area, right? dA integrated for the closed surface is A. And this A is this A of the sphere, right? The surface of a sphere, which is 4 pi times R squared. So the whole thing amounts into finding Q enclosed, because the remaining is same, right? 4 pi R squared times epsilon 0, and we usually write it like that. Okay, so we apply this formula for 4 different situations, where R is less than A, between A and B, between B and C, and more than C. Okay, so let's start with the first situation. So for when R is less than A, it is this one, right? Remember that all of the charge is located at the outer part of the sphere. So Q1 is just on the surface. And when R is smaller than A, there is no charge inside the Gaussian surface. So Q enclosed is equal to 0. Hence, E is equal to 0. Again, it's all finding what the enclosed charges are, right? So that's part 1. And for second part, when R is between A and B, what is Q enclosed? Now it's the second one, so let me even give numbers here. Okay, so this is like 1, this is like 2, the third one, and the fourth Gaussian surface. For the second Gaussian surface, so you see this is the Gaussian surface. The enclosed charge here is Q1, right? So it's just Q1. And therefore, the magnitude of E, the electric field at any point, is Q1 divided by 4 pi epsilon 0 times R1 squared. Okay? Not R1, sorry. It's R squared. Okay, so it is R squared, right? There's no index in here. That's for any R. And the third one, is the third Gaussian surface, which is this guy. Remember what we have here. I even draw it here, right? Q1 attracts same amount, but with a negative with the opposite charges, Q1 and minus Q1. And therefore, since you have this minus Q1 at the inner surface of this spherical shell, the total charge inside the third Gaussian surface is Q1 minus Q1, which is 0, right? So therefore, Q enclosed is equal to 0, or Q1 minus Q1, which is equal to 0. The magnitude of the electric field is 0. And finally, the fourth part is asking us what R is when R is greater than C. So it is this fourth Gaussian surface, which is up here, right? Now the total charge inside this is Q1 plus Q2, right? So Q enclosed is Q1 plus Q2, and therefore the magnitude of the electric field is equal to Q1 plus Q2 all divided by 4 pi epsilon 0 times r squared. Okay, so this is basically it. The whole thing is basically finding an appropriate Gaussian surface and then calculating the enclosed charge inside the Gaussian surface. Thank you.